Welcome to part 2 of high-level virtual machine implementations for CS263. Last time we were talking about the transfer format that Java programs take as they transfer over networks. We have on the left an example of Java source code. On the right, we have an example of Java bytecode. When you have Java source code and you use the Java C source compiler, what is produced are binary class files that have the format of the code on the right. On the right, I only include the bytecode for the main static method in the class simple. As you can see, and we've talked about in gory detail in the last lecture, the bytecode is arranged in byte order. That is the index in the right figure to the left of each instruction. For each instruction that accesses the constant pool does so with a hash symbol and an integer number. That number is an index into the constant pool where constants and symbols that the program uses are stored. The point I want to make in this example, because we've gone over it in prior meetings, is the operation, the opcode, or the opcodes at lines 13 and 16. Line 13 is a field access. In this case, it's putting a value into a static field. The field is indexed in the constant pool at number 4. And if we chase that index, we find that the field is field 2 in class simple. So the value, this instruction is going to consume what's on top of the stack, which has to be the value, and it's going to store that value into field 2 once we have an address for it when we're running in the runtime at the target location. In this case, instruction number 13 is consuming what was just pushed onto the top of the stack, the operand stack, which is a null value, and that null value is what's being assigned to the field 2 in instruction number 13. This bytecode corresponds to the assignment, field 2, the assignment on the left, the second from the bottom, this line here. The instruction invoke static is a static method invocation. If we chase the index into the constant pool number 5, we find that it's a method foo in class simple. Foo takes no arguments and produces a void return type. This instruction number 16 in bytecode represents the last instruction in the main function on the left. This invoke static takes no arguments, so there's nothing consumed from the operand stack when this method is invoked. There's nothing pushed onto the runtime stack when it is finished. I want to bring out the differences between static field accesses and method invocations and instance field accesses and method invocations in Java. In this example, we have a new Java source code class called hello with a main routine, and on the right is the bytecode for that main routine. If you look down at the end, there's a couple of points I want to make. Halfway down through the bytecode, we see the new instruction at index number 8. This corresponds to the new command in the source code on the right, the second instruction in main. Because Java's specification for the language says that allocations of objects is separate from the invocation of their construction, the initialization via constructor. There's a separation between constructors and allocation bytecodes. In addition, Java language specification says that constructors, the initializers of objects, return nothing. They don't return a value, so they can't return the object that they're constructing. So the way this translates in bytecode is such that the new command indicates an index into the constant pool, which identifies the class. This new command creates an object. That object eventually, when this program executes, will be allocated on the runtime heap. The address that is returned from that allocation is placed on the operand stack at this point. However, if at this point we called invoke special, that is, we passed in this new object reference to the constructor, what would happen is that constructor would pop that object off of the operand stack and initialize it. But since the initializer, the constructor, cannot return a value, nothing is returned, and therefore the object is lost. We cannot get to it. So what we need to do is duplicate the address from the new routine. So the new instruction creates the object and pushes the address of the object onto the operand stack. We then call dupe, which is an instruction which duplicates the top of stack. So at this point, after instruction number 11 in bytecode, we have two addresses on the top of the stack. They are the same addresses. Therefore, they are aliases of each other. That is, they refer to the same object out in the heap. That means if we operate on one and modify the object through one address, you can see the changes through the second address. So now we have two addresses on the top of the stack. The constructor, invoked by an invoke special routine, consumes the top of stack address, which is one of the addresses that has just been created as an object. It initializes that object and returns nothing. So when this instruction returns, the only thing that's on the operand stack is the duplicated address. This duplicated address refers to the same object that was just constructed, so we're okay, and we now have a handle to the object that we can use in the later opcodes. The first thing we do with that handle is to store the address of this object into local variable 1 at line 15 in bytecode. This corresponds to the OBJ variable in the source code on the left. The other point I'd like to make is to point out the differences between instance fields and instance method invocations in contrast to the static fields and static method invocations that we looked at in the prior slide. In this case, at line 19, we're putting a value into an instance field. An instance field is located inside an object. Every object has its own copy of its instance fields. So therefore, in order to put a value into this field, we must have an object. If you look at line 16 in bytecode, we're going to take the value, the address, that's in local variable array at index 1 and put it on top of the operand stack. This is the object reference that we've just constructed and which corresponds to the OBJ variable in the source code. So we first push the object instance that we want to access the field within. We then push the value that we're going to store in that field, and the put field consumes the object instance and the value and pops them from the operand stack. For instance method invocations, we also need an object instance. So at line 22, prior to the invoke virtual, which is a dynamically dispatched instance method, we're going to push onto the operand stack the object reference. The invoke virtual consumes this operand, even though if you look at the method signature for getField, it takes no arguments. When we have an expression in the source language, like on the left in the last instruction, where we say obj.getField and we pass in no arguments, that syntax is converted to have obj be a hidden first parameter, sometimes referred to as this in Java. So the this object is being passed, and Python is referred to as the self object. That's being passed behind the scenes as the first argument. So the parameter list doesn't show this argument or parameter in its signature, but we know that it's there because this method is an instance method. There is no static keyword on its definition. So again, instance field accesses and instance method invocations require an object instance to be on the operand stack prior to that instruction being executed. So that's it for our review. The next thing to consider is what happens to these class files once they transfer over a network and are loaded into the runtime system for execution at the target location. We're going to be talking about that next. In particular, we're going to study how class files, these files that transfer over the network, are converted to memory and represented in the memory of the virtual machine that's executing them. There's two important aspects of this internal representation of these entities in the virtual machine. They are the class model and the object model. The class model defines how classes are represented internally in the virtual machine, and the object model defines how objects are laid out once they are created and allocated and during execution. Another thing to remember is that everything is done with laziness because we don't want to do any work unless we ultimately have to, because we're doing a lot of work already in the runtime, given all of the abstraction and high level that these languages permit. So what we're going to do is we're going to load classes incrementally, one at a time, even if they're a bunch of classes being transmitted in a jar file, a Java archive. Only individual classes are loaded and given internal representations of the class at a time, one at a time, as they are used, as they were needed by the runtime. So as they are accessed if you access fields, if you call int methods, if you use the new operation to create objects, all of that causes class loading incrementally over the lifetime of the execution. In addition, whenever we need to execute a method, at that moment, just in time, we take that method and give it a home in memory. We can do this a couple ways. We can just copy the bytecode into memory and interpret that memory, or we can convert the bytecode to native code, assembly code of the underlying target architecture, and execute it without any interruptions. We'll talk about interpretation and compilation in the future classes. So as class files are transferred over the network or are touched during an execution of a program, they're loaded into memory. We need to have data structures in the memory of the virtual machine so that we can link different classes to each other. So if you have one class and it's invoking a method in another, we need to be able to load the first class and begin executing it, and only when we touch the second class, that is, we access the second class to invoke a method, do we load the second class. As these classes are loaded into memory, they're given memory locations, they're given addresses, and then we have to fix up the different addresses so that everything links together. All of the information in the constant pool in a class file is given a home in the memory of the virtual machine. And we'll talk about how that's done in the next few slides. In particular, though, we're going to simplify everything and have one large table that holds all things static. We'll call it the statics table, and different virtual machine implementations do different things, but all of them have some sort of mechanism, some sort of data structure that stores all of the static fields and static methods and all of the constants that are being brought in by the class files as they're being loaded and executed. We're going to refer to this as the statics table. All things static will be going into the statics table. In addition, if there are other data structures that the virtual machine needs, those data structures will also have a home in the statics table. In parallel to the statics table, we will have a map which will identify what is in each location in the statics table. So that's really easy to figure out what are the addresses of the various components of the program. Here's an example to get us started. On the left, we have a class file called parent. It has static fields and instance fields and 2 static methods. When this class is loaded into the runtime system, the memory of the virtual machine, all of its static members are added to the statics table. Statics table is represented by the box in the middle. The statics table has next to it, the statics map. This is a map of the names and the types and the offsets of the objects that are being stored in the statics table. So as parent is loaded, parent field 1 is in the map under name. Its location says SF, that stands for static field, and its offset is 0. So the value for field 1 in class parent will be at memory location 0, the same 0 off of the statics table. So let's say we put the statics table address in register R7, then at location R7 is where field 1 is located, and we know the size of field 1 because we know its type. The same thing goes for field 2. It's a static field. It's at index 4. So if we ever access read or write field 2 in class parent, we simply go to the address that's stored in register 7, R7, add 4 to it, and get the value of field 2. We can read or write it. We also store static methods in the statics table. Static methods are just addresses to code bodies. So we have 2 entries because we have 2 static methods, test1 and test2 in class parent. SM stands for static method. They also have offsets into the static table following the fields. The order can vary, but typically it goes from top to bottom in the class definition. In this case, both test1 and test2, the static methods in parent, have address 720 in memory. At address 720 is going to be code that causes methods to be copied and interpreted or compiled at runtime. So every method is given an initial value of a compilation stub or an interpreter stub, such that if the method is invoked for the first time, it will jump to the stub, and the stub will process the method for the first time, give it a memory location, a home in memory, and update its value in the statics table. We'll explain more about this and give you other examples later. Down below on the right, we show you the internal representation of the class. So all of the static fields and methods for parent go in the statics table, but we still need an internal representation of the class. The layout of this internal representation is the class model. Similarly to the statics table, we have the internal representation of the class parent, and we also have a map. The first byte the first word of the internal representation of class parent is an address to this map. The internal representation in this example is at 90A, an address in memory. The map is at 920, an address in memory. 920, the value is stored in the first word of the internal representation of the class parent, so that it's easy to get to. This internal representation, in particular, the map, holds all things instance. So in this case, we have 2 instance fields. We put field 3 and field 4, IF stands for instance field, at different offsets. Those offsets are not offsets into the statics table, they are offsets into the object itself, because instance fields are stored with the object. These data structures, the internal representation of the class parent and the map for parent, need to be easily accessible from the virtual machine. And so typically what happens is we add these addresses, these data structure addresses, to the statics table and add them to the map. In this case, the parent type is at offset number 16, and it is the class type info object, that is the map for the internal representation of class parent. We also add the representation itself, the address of the representation. We're going to put that in the statics table at index 20. And again, this is all just for easy access. All the data structures that the VM needs are here, and it's easy to find them using our map. Next, if you think back to our review last week, we have static methods and fields, and like I just said, we're going to keep those in our statics table in the runtime. Whenever we need to access a method or a field in a class, we simply use the map for the statics table to look up the offset, and we use that offset in the code that we will ultimately generate, or in the interpreter when we're executing the code line by line. This is similarly done for both static and dynamically typed languages. Instance fields are fields for which every object instance has a copy. Instance fields are statically typed, which means that we look at the type of the variable that holds the reference to the object to figure out what field we mean. If there is inheritance and there's a field with the same name in both a parent and a child, the child holds memory locations for both. That is, both are available. The names are just hiding each other. So, like I said before in a previous lecture, instance fields are hidden in an inheritance hierarchy, not overridden. So if they're hidden, we have to have a location for both. If we use the object if the variable type, we can access the child version, assuming that the variable is of type child. If we want to get to the parent field that's being hidden, we just cast the child type variable to the parent type to access that field. This is completely different from a dynamically typed language where we do all lookups by name and we have a hash table per object. We're going to focus on statically typed languages, Java in particular. The next thing to remember from our review is that instance methods can be statically dispatched or dynamically dispatched. Statically dispatched methods are found in the same way that instance fields are found. We have copies of both. We have instance methods that we access through the variable using its type or its casted type. If we have statically dispatched instance methods, then they would be stored in a statics table. We don't have to look anything up at runtime. We know exactly what instance method we're invoking by looking at the type or the casted type. In Java, only our constructors are statically dispatched instance methods. They're statically dispatched because we know exactly what constructor we mean. We say new, the name of the class, and some signature for the method. We know exactly from that signature, the name and the signature of that method, what method you want to invoke to construct or instantiate the object. And so that method can be statically dispatched. We know exactly which one it is. However, it operates on an object instance, so therefore it's an instance method. All other methods are dynamically dispatched in Java, similarly to methods in C# that are marked virtual and methods in C++ that are marked virtual. This slide shows the object layout. Every object holds the fields, the instance fields that it implements. However, there's also a header for every single object. It's at least one word, and it can be multiple words in length. We'll use this header for lots of different purposes. In particular, we have to use the header to indicate what the type of this object is. This way, we know how big the object is. We know what class internal representations to look at to figure out what our offsets are. The object model is what specifies the object layout in memory, and in particular, the object header configuration. This header can hold lots of things. We'll use it throughout this class. The reason we're looking at it today is because it's going to tell us what the type of the class is, what the class internal representation is, so that we can figure out what our offsets are to the field that we want to access. The header is also used for garbage collection, for locking and synchronization, and for hash codes if you use hash codes in Java for unique identification of objects. Back to our picture. In our header, we're going to indicate what the type is of this object. The way we're going to do it is we're simply going to put the address of the internal representation of the class that this object instantiates. So in this case, the first word of the object is going to be 90A, which is the address of the internal representation of class parent, because we know that this is an object of type parent. We indicated it with a new instruction, new parent. Now that we have this connection, we're able to figure out what the type is of this object, and having that information, we can take an offset from the top. We can figure out what offset we want to access in order to access our fields. Again, every object instance will have a similar header and all of entries for its individual fields. For instance methods, we talked earlier about the difference between static dispatch and dynamic dispatch. You can pause here if you'd like to review. With dynamic dispatch, we're going to have to look up the type of the object at runtime to figure out which method we want to invoke. That is, when we inherit an instance method that's dynamically dispatched, it's overwritten, not hidden. And so we're going to inherit a method, and if the child implements that method of the same name and signature, it's going to replace the one that it inherited from the parent. And this way, we're going to be able to perform dynamic dispatch pretty efficiently. The way we're going to do this is referred to as a dynamic dispatch table. These are the addresses of methods that are going to be dynamically dispatched. There are dispatch tables in every object-oriented language that has dynamic dispatch: C++, C#, and Java. We also refer to this table as the virtual method table. Again, this is just a table that holds all of the addresses of the methods that are defined in the class as instance methods that are dynamically dispatched. We could put these addresses in the object itself, but there's a difference between the addresses of methods and fields. Fields are modified. They're read and written and can change over time. Methods, once they're compiled, rarely change. They're not modifiable by the program. And so what we can do is, instead of having more space in every object, which can take up a lot of memory, we put the virtual method table, that is the list of addresses for all of the instance methods that an object can invoke, in the internal representation of the class. So this VMT, or this dynamic dispatch table, is inside the internal representation of the class. All object instances, as we learned from earlier slides, refer to this internal representation of the class. So now, in order to invoke a virtual method, we need an object. We need an object instance. We have that object instance. We take its first word in the object, which is in the header. We use that address to access memory, and we take an offset from that address to get to the virtual method that we want to invoke. So this way we implement dynamic dispatch. When we invoke a method, we consume an object, we go through the object's header to get to an offset of the method we want to invoke. This way we can guarantee that we're invoking the method implementation of the underlying object to which the variable refers. Let's look at the example. In this example, we have the class parent, which we saw before. We have our statics table. We also now have a new class called child. Child extends parent. That means child inherits from the parent class. So one thing to point out here is that when child is loaded. It will be the first class loaded because it has the main method. What we do, because upon being loaded, it hasn't touched parent, but because child extends parent, that means the child will have to inherit all of the parent parts. We have to also load parent, and this will happen all the way through the hierarchy. So if you load a class, it's going to load the entire hierarchy above it so that it can get all of the fields and methods in the lowermost child object. Okay, so we've loaded class child. That triggered the loading of class parent, and we put all things static from parent into the statics table. We then do the exact same thing for child. We added to the statics table field 2, method test2, and method main. Just like for the other methods marked SM in our VM statics map, we originally put the address 720 for the method. This is an address in memory for what's called the compiler stub or the compilation stub. You should think of it as a wrapper. It's a piece of code that, when it's actually invoked, is able to look up what method is being invoked at this moment and compile it, put it into memory so that we can actually interpret it or execute it natively. So in this example, we've done this process. Main is the first method about to be executed. Upon invoking main, the stub at 720 was invoked. We had a hidden parameter to indicate that we wanted method main. That compiler stub, that wrapper, compiled method main, or grab the bytecode and put it into memory. Either way, we'll talk about the differences between interpretation and compilation in future classes. But either way, main now has a new address. It's the location in memory where the code is. So we removed 720 and we updated it with 523, the address in memory at which main is stored. We next create our internal representation of class parent and its map, the same as we did earlier, only this time we are able to add our instance methods. In this figure on the left, we have 2 additional instance methods, test3 and test4. You'll see in the map for the internal representation of class parent, we've now added test3 and test4 to the map. They're marked IM for instance method, and they're given offsets into the VMT, the virtual method table, or the dynamic dispatch table of class parent. So at offset 4, from the top of the internal representation of class parent, address 90A, we have an address to the compiler stub. It's an address to the compiler stub, the wrapper that's going to load test3 into memory once we eventually execute it. But we're not going to load it ahead of time because that would be premature, and we do everything lazy to save work where we don't have to do it. Test4 is exactly the same. Its offset is at offset 8. Notice that in the map, field 3 has an offset at 8, and test4 has an offset at 8. Field 3 is an instance field, so its offset is in the object. Test4 is an instance method. It has an offset into the virtual method table. That is, it has an offset into the object that is the internal representation of class parent. We do the same thing for the child class. We make an internal representation of the child class, and we have a virtual method table for its instance methods. If you look at the map on the far right for child at address 0x975, you see we inherit all of the fields of the parent first. We then store and make offsets for all of the fields in the child. Even if the field names are the same, we have both because instance fields are hidden and not overridden. So we can access field 4 in the child, or through a cast, we can access the field 4 in the parent. The next thing is we do the same thing for instance methods. We inherit, we copy, and make homes for all the things that come from the parent that are instance methods, namely test3 and test4. Only this time we do something a little bit different when we start to consider the instance methods in child. In particular, we don't just add test 4 from child like we did for fields. In this case, we overwrite test 4 because methods are dynamically dispatched. And so they overwrite the inherited versions. We inherit test 3, and that stays the same. That'll be the same method that's in parent. And test 4 will be child's version of the instance method test 4. And then we add any other instance methods in the child to the map, and all of those are given homes in the virtual method table. Next, I just moved everything up to give us more space. These are all of the things that we've just went through. I've now taken the data structures that the virtual machine, the runtime system, has created for itself and added those to the statics table. Namely, I added the internal representations of class parent and class child and their maps. So I've added parent type, that is the map for the internal representation of class parent. I've added parent rep at index 32 of our statics table. That is the internal representation of the class parent. I've added child type, which is the map for the child at address 975, and I've added the representation of the child class which is at address 91C. The next thing I add here is the method main, and there are instructions in main. I've written them in source code here. One thing to note here is that I'll be referring to the point of execution in code. We're going to call that the PC for program counter or execution point. And all this means is that this is the point in the code that is executed so far. So this blue arrow indicates that we have executed that first instruction in main and stopped immediately thereafter. So that's where we are. And so that way we can look at memory and see what memory looks like at that particular moment. The first instruction in in the method main, allocated an object in the heap. This is going to be the runtime heap. So when this actually executes, it's going to be the runtime heap of the VM into which a parent object is created. We then call the parent constructor, the default parent constructor, and the combination of those two things produced the object that the variable L1 of type parent is pointing to. So in the code on the operand stack, what you have is an address throughout this process and afterwards that is value 1010. This is the reference that variable L1 holds. This is the reference to the object. If I ever access a field from this variable, we're going to go to address 1010, add an offset, and access the field. Now let's say control transfers down. We've executed the entire method main. So we've executed all 3 instructions. What I have here are orange arrows that would point to the object representations in memory. These are objects that have been allocated in the heap, the runtime heap of the virtual machine, and have been initialized with the constructors. The second 2 objects are initialized with the child constructor. Notice that the second variable, L2, is of type parent, but it holds a child. This is fine because anything that variable of type parent holds can only access parent parts, and we're guaranteed that child objects, in this case, will have parent parts. We notice that the fields are different in the child objects from the parent objects, but they're the same across the 2 child objects because I haven't done anything but create the object instances. Notice that in each of the objects that I've created, we have the header, which is one word that points to the internal representation of the class, and the rest of the header, and then the fields start thereafter. If we want to know what field is what, we simply go look at the map for the class that's being referred to at index 0 of each object. Your exercise with assignment 3 is do the exact same thing for the code in this slide. We have 2 classes. They have static fields and methods, and instance fields and methods and constructors, all of which you can formulate in the memory of the virtual machine. I give you a handout on the web page that looks like this for you to fill in. At the bottom, we have all of the method addresses so that we can have a unified addressing. The compilation stub is at address 789 in the bottom left. If you look at the handout, I describe what addresses are where, and this slide sets all of that up for you. So now you can fill it all in with the information and the details from the methods and classes that I defined here. So we'll go through this all in class, do it yourself, fill in everything, and at the very end there's an extra credit question that talks about what happens when we're in main and we invoke the method invocation M2 on the variable temp A2. This slide describes all of the steps that one goes through to invoke M2 on variable temp A2. The idea here is that we're going to take the variable and get the address that it holds, because all object variables, all object instances hold references to those objects. So those variables hold references to the object. So temp A2 holds the address of an object. And so we go to the memory at this address, that is the address that the variable holds. We go to offset 0 so that we can get the address of the internal representation. This is going to get us to the virtual method table. We're going to go to the virtual method table because M2 is an instance method, which is dynamically dispatched. Once we get to the internal representation of the class, we take an offset of it to get the address of the method. We get the address of the method from memory, and if it's not compiled, that address will be 789, and then that will eventually compile. We'll at that point compile it, and the new compiled address is going to be 1040. This is just part of the description of the problem layout in the assignment. And once we get that address 1040, we can call the method and invoke M2. The second part of the extra credit talks about what happens when we invoke M1. M1 is a static method in class A. It's a little bit different. In this case, we don't need the object at all because it's not an instance method. It's a static method. So we're going to get the address of this method in the global statics table. We're going to look up using the global statics map the offset of method M1 in class A. This offset is 8 in this example. At offset 8, we go to the memory at the start of the statics table and we add 8, and at that location we grab the value there. That value is an address. That address will be 789 if the method has not been compiled yet. We're going to jump to that address, calling the compiler stub, which causes the method M1 to be compiled, and it's going to replace the address once it's done compiling it with address 0x1200. And then it's going to invoke the method at 0x1200 to invoke M1. Future invocations of M1 and future invocations of M2, either way, once they're compiled, will jump directly to the compiled method because the address has been overwritten at their offsets in the appropriate data structures.